Some integrals are much easier to do if you convert from rectangular or Cartesian coordinates into polar coordinates. Sometimes it gets harder, but sometimes it gets easier, and so you should be able to identify when one happens and when the other happens. The best thing to identify when it's going to get easier if you convert things into polar is if you have lots of x squareds, y squareds, and particularly if you have factors of x squared plus y squared, because that there is going to turn into r squared. Square root of x squared plus y squared is okay too, because that turns into r. So this right here is a prime candidate for converting into polar coordinates, because this is going to be 18 minus 2 times r squared. Okay? So first of all, let's come up with a description of the domain of integration using polar coordinates. We'll draw things in 3 dimensions. This is going to have a z-intercept of 18, right? And it's going to have, well, think about where it intercepts, for example, the x-axis. It's going to curve down parabolically and hit right there. Along the xz plane, which is where it's going to hit the x-axis, along the xz plane, y is 0 the whole time. So this will happen when, if y is 0, then z equals 18 minus 2x squared. And if we want to know when it will hit the x-axis, that's when z equals 0. It'll be 18 minus 2x squared equals 0. Rearranging this, you'll find that x equals positive or negative 3. So really, this is going to happen 2 times, and we knew that. It's going to happen once on the positive and once on the negative. Because the x and the y are symmetrical, we know that it's going to behave the same exact way along the y-axis. It's going to hit 3 and negative 3 along there. So the domain of integration is actually a circle with a radius of 3. And a circle with a radius of 3, it's kind of, in the way that I wrote it already, it's super easy to describe in polar coordinates. That is simply r equals 3. So we're going to be integrating over a domain that sends r from 0 to 3, as in the interior of the disk, right? And then theta, because it is the entire disk, theta is going to go from 0 to 2 pi. That means you cover the whole thing, and you cover it exactly once. All right, so let's rewrite the integral, or, well, let's write the integral in the first place. We haven't written it in the first place. So we're going to say integral of f of x and y dA over this domain. That's going to turn into integral over the same domain of f of r and theta dA, but remembering that when we turn it into an actual like dr d theta, we're going to have to include the r factor there. It's going to be r dr d theta. So this is going to be integral. It's customary to do theta last. So we'll say that's the outer integral from 0 to 2 pi along theta, from 0 to 3 along r. And this is 18 minus 2 r squared, because that's what that is, right? 18 minus 2 times quantity r squared. Don't forget, though, r dr d theta, not simply dr d theta. If you don't include the r, it's wrong. Because this is already a polynomial in R, we can really just say that this is going to be included by, make that smaller. We can say that this is going to be included just by kicking this up to R and this up to R to the third. All right, so the inner, from this point on, it's a pretty routine problem because you're really just integrating a polynomial, but we'll get through it. The inner is from 0 to 3 of 18r minus 2r to the third dr. This is going to be 9r squared minus, and then r to the third goes to r to the fourth over 2 or over 4, but times 2 will be r to the 4th over 2. And this gets evaluated as r goes from 0 to 3. The 0 will go away. So this is going to be 3 put in for 9 times r squared is 9, minus 3 to the 4th, 3, 9, 27, 81. 81 over 2. 9 times 9 is conveniently enough 81. So 81 minus 81 over 2, that's 162 over 2 minus 81 over 2, or 81 over 2. For the outer, if you're really, really paying attention, you may know how this is going to end already. It's not strictly necessary to do this, because if you integrate a constant function over any interval, it will be simply the value of the constant function multiplied by the length of the interval you're integrating it over. But let's see that happen in real time. 81 theta over 2, and then theta goes from 0 to 2 pi. Well, the 2 pi is going to get swapped in to get 81 times 2 pi over 2. The 0 zeroes out. The 2's go away. And so this is going to be 81 pi. Of course, this is the same as if you said 81 over pi multiplied, 81 over 2 multiplied by 2 pi for the length of the interval.